Hi everyone, I'm Guruswamy Revana, working as Associate Professor in the Department of Electrical and Electronics Engineering. Today, my topic is about EMF equation of the transformer. So the basic prerequisite for this topic is to know the concepts of magnetic circuits. Along with that, the student should be aware of principle of operation and working construction of a transformer. Now coming to the EMF equation of the transformer, as we all know, for the primary the supply is given for a transformer, which is a sinusoidal supply. So it is being excited by the sinusoidal supply. As the primary circuit is closed, a sinusoidal current starts flowing to the primary winding of the transformer. So this sinusoidal current produces a sinusoidal flux, which is according to the waveform as shown in this figure. So there is an alternating flux, which is sinusoidal in nature, is being produced in the primary of the transformer. So the equation of that alternating flux is given by phi is equal to phi m into sine omega t, where phi m stands for maximum value of the flux. And in the equations, we are going to come across certain kinds of symbols or the alphabets like F, which stands for frequency of the supply voltage. N1 is number of turns of the primary winding. N2 is number of turns of the secondary winding. E1 is the RMS value of the primary induced voltage, and E2 is the RMS value of the primary induced voltage. So with this, we continue with the derivation of the EMF of the transformer. According to Faraday's laws of electromagnetic induction, the EMF induced is given by E is equal to minus N into d phi by dt. In place of this phi, I am going to substitute my sinusoidal equation, where phi is equal to phi m into sine omega t is being substituted here. Phi m being maximum value, it comes out of the derivation. So it is totally written as n minus n into phi m into differentiation of sine omega t. So the differentiation of sine omega t is cos omega t into omega. So finally the equation reduces as E is equal to minus n into phi m into cos omega t into omega. This is the differentiation of the sine omega t. But this cos omega t can be written as sine omega t minus 90 degrees. So finally the equation comes in this way as E is equal to minus n into phi m into omega into sine omega t minus 90 degrees. So I reduce this equation. I want to write the equation as a standard voltage equation as E is equal to Em into sine omega t plus or minus 90 degrees. So I write this n phi m into omega as Em, where Em is the maximum voltage or the peak voltage, which is called as n phi m into omega, where phi m stands for the maximum value. So with the maximum value, I want to find out the RMS value of the voltage being produced. From the circuits, it's very clear that RMS is equal to maximum value divided by root 2, or VRMS is equal to Vm by root 2. I use the same formula for the EMF induced voltage. ERMS is equal to Em by root 2. In the previous session, we just found out like Em is equal to n phi m into omega. So I substitute my n phi m into omega here. So divided by root 2. But we know that omega is equal to 2 pi f. So I substitute my 2 pi f here. So finally the equation reduces as 2 pi into n phi m into f divided by root 2. So if I calculate this 2 pi into root 2, because they are constants, I find out what is the value of 2 pi divided by root 2. So the ERMS is going to come as 4.44 into number of turns into frequency into this maximum value. So this is the RMS value being produced. Now I'll find out what are the EMF induced from a primary and also the secondary. So the RMS value of the EMF induced for the primary winding is E1 is equal to 4.44. The turns of the primary winding N1 into phi into F1. Previously I got a generalized equation. Now I separate this equation for the primary as well as the secondary. So primary is E1, where the number of turns are N1. The frequency remains the same. It is unaltered in a transformer and the maximum flux is always there. And the EMF induced in the secondary winding is given by E2 because it is a secondary winding. I term it as E2. E2 is equal to 4.44 N2, number of turns of the secondary into frequency into Fm. So 2 and 2 are going to remain same because it is a secondary winding. So basing on this, I go with the transformation ratio, which is nothing but secondary induced voltage divided by the primary induced voltage with the previous equations. You can look at this one, all the constants like 4.44 F and the maximum value of the flux gets cancelled. And we are finally left with E2 divided by E1 is equal to N2 divided by N1. And here we get a new term called transformation constant, which is called as K. So basing on this transformation ratio, which is nothing but the K, we have two kinds of transformer called step-up transformer and step-down transformer. If this transformation ratio is greater than 1, it is called as a step-up transformer, where you can see here the 100 volts which is in the primary is being stepped up to 400 volts. And if K is less than 1, it is also called as a step-down transformer. Here with an example, so the primary has 1 kilovolt, which is being reduced to 200 volts. You can also observe from these two things, when the voltage increases, the current is decreasing. From 100, it has increased to 400 volts. The current has reduced from 10 amperes to 2.5 amperes in order to maintain the constant power. And in the similar way, step-down transformer, when the voltage is being reduced, you can see the increment in current, so that you know the total V1 into I1 is equal to V2 into I2. So this is the derivation and transformation ratio of a transformer. Now let me tell you the activities which are being conducted for this basic electrical and electronics engineering subject. So we generally take the students to open source learning, so which is nothing but taking the students to different places in the campus where transformers of various ratings are being presented. So this is one of such transformer which is present in our campus, and we inform them with basic technicalities and make the subject most interesting. We also take the students to another transformer, which is 11 kVA by 450 volts transformer, which is present before our college, and make the subject more interesting to the students. And we make them to know the importance of the nameplate details, and we also make them to study and write a report on these things. Apart from that, we also take the students to industrial visit. Here is one such industry called Hammond Power Solutions Limited, a Canadian-based industry, which manufactures three-phase industries of various ratings. So we take them for a half day for the industrial visit. On top of it, we also do something called Google Class, where we send information regarding to transformers. It's all about the videos which are present in the YouTube, the useful videos, and we send the material to it, and we also keep tests with the Google Sheets. And this is one of the work done by our students in order to know the construction of the transformer with different things. So this is all about the transformers, and thank you very much.